Game-playing AI usually learns by playing millions of rounds. This one barely plays. It writes a copy of the game, tests its theories inside the copy, and only then makes a move, finishing 179 levels out of 183, on most of them in fewer moves than the humans who went first. The benchmark is called ARC-AGI 3. Every game is a 64 by 64 grid of colored cells. The controls are never explained, and the win condition is hidden. People work these out in minutes, and frontier models mostly fail. When researchers at Stanford, Cornell, USC, and Yeshiva University handed one of these games to a strong coding model, it scored 7.8 out of 100. So instead of asking it to play well, they asked it to write a program that predicts what the game will do next. The system is called Twin. Instead of picking a move, the coding agent writes an executable copy of the game in Python, a step function that takes the grid and an action and returns the grid you should get back. Then comes the rule that makes it work. Before the agent may touch the real game again, that program has to replay every transition it has already seen and reproduce all of them exactly. Here is the loop. Everything left of that boundary is free because the benchmark does not score thinking, so the agent can simulate and rewrite its code as much as it likes. It observes a frame, writes the twin, and validates it against the entire log, where one wrong prediction rejects the whole program. Then it plans inside the validated copy and submits a single move. If the real game disagrees, the run halts and that mismatch repairs the code. Which raises the obvious objection. A program can match a log perfectly and still have understood nothing, so the authors went looking for whether these copies predicted situations they were never shown. They took each finished twin and fed it state and action pairs the agent had never tried, then ran the real game engine on those pairs and compared. The bar was brutal. A prediction counted only if all 4096 cells matched, so one wrong square anywhere failed the whole frame. The bars on the right pool every game. Replaying transitions it had already recorded, the twin is right 99.4% of the time. On pairs it never observed, it still predicts the exact next frame 70.1% of the time. Each dot on the left is one game, and the filled circles are that harder unseen test, so you can see the spread from copies that nail almost everything down to one that barely generalizes. So the copies carry rules, not recordings. But this benchmark does not award points for understanding a game. It awards them for how few moves you need. The score compares the agent against people playing each game for the first time. Clear a level in fewer moves than that human baseline and you score well, flail around, and the score drops. This is where planning inside a validated copy earns its keep, because a wasted move inside the simulation costs nothing, and only moves that reach the real game are counted. Every dot is one game. Human moves run along the bottom, the agents up the side, and that dashed line is parity. Green dots sit below it, meaning fewer moves than the first-time human, and 21 of its 23 cleared games land there, averaging about 6/10 of the human count. The two red dots above are games where it misread what it was meant to do. Two things keep this honest. The validation trick works because these games are deterministic and the board is small and discrete, so checking 4096 cells for exact equality is cheap. With continuous or noisy observations, each check becomes an approximate comparison with the threshold somebody has to tune. And this is not the top score on the benchmark. A rival system on a stronger base model reaches 95.5. What Twin shows is what a harness does to a fixed model, taking the same one from 7.8 to 61.1 in a standard harness to 93.3. Here is every game with Twin in blue against the two closest published systems. Down the easy half, everyone clears. The gaps open on the awkward games, like the one that hides most of each level behind a scrolling camera, where the rivals collapse to near zero. Twin clears all 9 of its levels under the human move count, by spending a probe to buy back each piece of the map it cannot see. The authors expected the world model to be the hard part, and it wasn't. Their programs recovered the mechanics of a hidden game almost every time, from a few hundred moves. What stayed hard was the goal. On the levels that cost the most, the agent knew exactly what its actions would do and still had to search for what the game wanted. Learning how a world works is the tractable half. Knowing what to want inside it is the part still missing.